Hello, this is lesson 15.2 on double integrals over general regions. So now that you know how to do double integrals over rectangles where the sides are parallel to the coordinate axes, we're going to generalize this to double integrals over any geometry, any domain of any geometry. Double integrals over general regions, we're going to consider two different types of regions, which we call type 1 and type 2 very simply. I'll put them here side by side so you can compare and see the differences between these two kinds of regions. So a type 1 region in the xy plane is a region that is bounded between two constants in the x direction, a and b, and two arbitrary curves in the other direction. So you can call this curve y equals g1 of x, and this one y equals g2 of x. And so this defines a region D right here. So D is defined here by, it's a region where x is bounded between two constants a and b, and the y-coordinate, it's bounded between these two variable curves, g1 of y, or g1 of x, and g2 of x. Okay, so that's type 1, and type 2 is where everything is reversed. So now we're going to take two constants in y and call them c and d, and two arbitrary curves in the other direction. You can call this one x equals h1 of y, and this one x equals h2 of y. This again defines a two-dimensional region D in the plane. Now the y-coordinate is trapped between two constants c and d, and the x-coordinate is between two variable curves, h1 of y and h2 of y. So now we want to integrate a function of two variables over a domain of either kind. So let's take a function f of xy. So the way you integrate a function over a domain D, if you have a type 1 region, then you are going to first integrate using vertical strips of width dx, and you're going to sweep up and down between the two variable curves, which means this integral goes on the inside between g1 of x and g2 of x. So going in the y direction, and then once you have this strip done, you go in the other direction and sweep the rectangle right and left between a and b in the x direction. So you obtain a double integral written in this way. If you have a type 2, everything is reversed. So you have the same function, but now you're starting to integrate in the x direction first, which means you are integrating in this direction parallel to the x-axis, a little strip of width dy between the two curves h1 of y and h2 of y. And when you have done that, you can sweep this up and down between c and d in the y direction. Okay, so here are the two ways that you can write a double integral for type 1 and type 2 regions. Okay, so some of these areas are actually both type 1 and type 2. I'll show you an example. So if you have a region that kind of looks like this, where you have a straight side here and a straight side over here, and some curve, so this region is bounded between these three curves right here. So in this case you have A and B are the extreme points in the x direction, and you have C and D are the extreme points in the y direction. And this curve right here can be written y equals g of x, or you can also solve it for x and call it x equals h of y. Depending on what you do, you get a type 1 or a type 2 region. You can consider this to be a type 1 region where x is bounded by the constants a and b, and y is bounded by the constant c below and the curve g of x above. You can also consider this to be a type 2 region, where in this case y is bounded between the constants c and d, and x is bounded between a on the left and the curve x equals h of y on the right. So because of geometry of D, you can choose when you integrate whether to write the integral as a type 1 or a type 2 integral. So some of these regions are also neither type 1 or type 2. In that case, you need to cut them up into type 1 and type 2s. So neither type. But all of them can be divided. And so when you divide them into a union of non-overlapping type 1 and type 2 regions. So for example, if you have a region that has a very strange geometrical shape like this, this is neither a type 1 or a type 2, but you can split it up, for example, this way and this way. So here you've got D1, D2, and D3. And you can consider each one of these, D1, D2, and D3, to be either a type 1 or a type 2. So in this case, the whole region D is the union of D1, D2, and D3. So if you want to find a double integral of a function over the whole domain, you write it as a sum of 3 integrals over the subdomains D1 plus the double integral over D2 plus the double integral over D3. No matter what geometry you have for D, you can always split it into type 1 and type 2. So all you have to know is how to do type 1 and type 2 integrals, and you can integrate any geometrical shape that you may ever encounter. So to look at an example, let's say we want to integrate the double integral over D of the function x cubed y, where D is the region bounded by x equals 0, y equals x squared, and y equals 4. So in this case, you really have to do a little drawing to see what the domain looks like. X equals 0 is the y-axis. Y equals x squared is a parabola that looks like this, and y equals 4 is a line like this. So here we have our region of integration. So this point is right at x equals 2, and this is the curve y equals x squared. Okay, so if you look closely, this region D is actually both types. It can be written as a type 1 or a type 2. You can write it as a type 1 by considering that x is between 0 and 2, and y is between x squared and 4. So here we're looking at a vertical strip like this. And so the bounds in the y direction are this curve in the bottom and y equals 4 on top. And then the bounds when you sweep this rectangle right and left is going to be 0 and 2. You can also do everything the other way, type 2. In this case, y goes between the constants 0 and 4. And x is bounded by the two variable curves 0 and this curve here solved for x, which is x equals square root of y. So the way you calculate this integral, depending on whether you choose type 1 or type 2, will be different. If we choose the type 1, that means we are first integrating in the y direction, so we put the dy inside and the dy on the outside, where y goes from x squared to 4 and x goes from 0 to 2. And from this point forward, it's just a nested integral, just like what we know how to do, except that one of the bounds are on the inside are not necessarily constants anymore. So in this case, if you integrate in y, you get y squared over 2. When y goes from x squared to 4. So plugging in y equals 4, we obtain a 16x cubed minus an x to the 7th. That's the first step, and then for the next step we do the integral in the x direction now, which is 4x to the 4th minus x to the 8th over 8th between 0 and 2. 1/2 64 minus 32 equals 16. Okay, so you know from Fubini's theorem that if we were to choose the reverse order of integration as a type 2, we should get the exact same result. Just to illustrate that, we can do it here, since we have the option of doing it two ways here. In this case, we are reversing the order of integration, which means we start by the direction in x and then do y, so the dx and dy switch places from which they were before. The bounds for x now are the variable bounds from 0 to x square root of y, and the bounds in y are the constants 0 to 4. If we proceed here with the integration now in x, it gives you x4 over 4, where x goes from 0 to square root of y, which is the integral of y cubed minus 0 dy. And for the second integral now, it's y4 over 4 between 0 and 4. And this gives you 16 again. So this just confirms Fubini's theorem, which is a theorem that says that you are allowed to switch the order of integration whenever you have a double integral. Okay, you'll have similar exercises of this kind in the problems.